All right, so our new unit is going to be called Modern Physics. And all the physics that you learned thus far, most of it was built, the basis of which was built in the 1600s or even earlier than that, right? They're called Newtonian mechanics. Newton, yeah, Newton 1600s. So, and now we're going to delve into stuff uh, from the 1800s to present day. Obviously, right? It's called modern physics for a reason. Now, one of the biggest questions, one of the biggest questions in the early 1800s was whether or not light was a wave or a particle. And this is a big question because if you know what properties light has, you can predict how it's going to behave. And so, as a refresher, waves are disturbances of energy that oscillate around equilibrium point, right? They go up and down, up and down, up and down. Uh, and they only transfer energy, right? The particles themselves don't really move anywhere. Whereas a particle can be defined as something of discrete energy, right? You know it has certain properties that don't change, right? It has certain physical or chemical properties and specific energies. So they don't really change at all, right? They don't oscillate. Now, in the 1801, uh, a double slit experiment was performed by Young. I forgot his first name, but his last name is Young. And so, well, if light were particles, right? If light were particles, then well, if you shine light through these slits, well, you're only gonna get this thing right here, this line of bright light. This line of bright light, as referenced here, right? If you're only shining through small slits, you're only gonna get a light pattern like this. Whereas if light was a wave, well, we know waves diffract as they go through slits. So if light was a wave and it passed through these slits, well, what you're gonna see is you're gonna see this pattern. You're gonna see this pattern. Now you didn't learn this last unit, but this is called a diffraction pattern. It's called a diffraction pattern. Well, I'll explain what this is later on. But right now, the only thing you need to know is that if you're a wave and you go through these double slits, well, what's gonna happen? You're gonna diffract. The light is gonna diffract. And so this is a simulation of what would happen if light was a particle. Right? So if light was a particle, then you would just see two bands of light. Just two straight bands of light. Now, if light was a wave, what's going to happen is that you're going to see light diffract. And when you see light diffract, you're going to see these patterns, this interference pattern on the backhand board. Well, why does that happen? I'll let this video explain.
Consider the bright spot in the middle. The light from each slit has to travel the same distance to reach that point, and hence both waves arrive in phase. That means crests with crests and troughs with troughs. So they add together and create an interference maximum, a bright spot.
I'll play it again.
Consider the bright spot in the middle. The light from each slit has to travel the same distance to reach that point, and hence both waves arrive in phase. That means crests with crests and troughs with troughs. So they add together and create an interference maximum, a bright spot.
This is called constructive interference, if you forgot.
There's a dark spot. Now that's because light from one slit has to travel on an angle, and it has to travel an extra half a wavelength compared to the light from the other slit, which means when this light is arriving as a crest, the light from the other slit is arriving as a trough, and so they cancel each other out.
So what's being explained here is destructive interference, and that's why you see these dark bands over here. And so we'll play it again.
There's a dark spot. Now that's because light from one slit has to travel on an angle, and it has to travel an extra half a wavelength compared to the light from the other slit, which means when this light is arriving as a crest, the light from the other slit is arriving as a trough, and so they cancel each other out.
So And so if it's a particle, it's going to behave like this. Light is going to behave like this. And if it's a wave, light is going to behave like this. It's going to create an interference pattern.
Consider.
So let's move on to this video.
What is light?
What is light? What is light? That's a good question,
So
isn't
this
it?
person
What is light?
This person is going to recreate the double slit experiment.
Isn't it an element?
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are.
It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The colour.
It goes in your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right?
Yeah.
It would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today, Thomas Young's double slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of a card, about 1/30th of an inch
in breadth,
and observed its shadow, either on the wall or on other cards held at different distances. Besides the fringes of colors on each side of the shadow itself was divided by similar parallel fringes.
smaller dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
And you can take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm gonna place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we gonna see on the bottom
Well,
of
the
the
obvious
box?
thing you think you're going to see is you're going to see two lines.
Two lines on the bottom of the box. Two bright bands.
Two little lines.
Yeah.
I think it'll be one line instead of two.
I could expect to see the whole box lit up.
That'll probably be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No.
I see dots.
How many?
It's one circle.
Well, there's one in the middle strongest, two either side.
The two on the outside are multicolored, and the one in the middle is just white.
It's kind of a rainbow.
The rainbow of colour as well.
Quite a few colours and lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
Let's actually
slits.
go
two
back a
slits.
bit.
Incredible.
So you see, again, you see the interference pattern here. You see an interference pattern here.
And that's just nothing else apart from
Two slits.
two slits. I can't believe- That's incredible.
But all we're doing is we're putting a light through two very narrow slits side by side. So how does this make any sense?
There's some kind of principle involved there that the average person is not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wave fronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there.
If you forgot, crests are the top part of the wave and the troughs are the bottom part of the wave. Right? So if you match crest with crest, what's going to happen is going to have constructive interference. Right? You have two tops or two bottoms. But instead, if you have a top part of a wave combining with a bottom part of a wave, well, they're going to cancel each other out. And that's what's happening in the middle here. That's destructive interference.
It's light canceling itself out.
This is basically the same as like having two drops of water fall in a swimming pool.
That's right.
Get exactly the same
and then
pattern.
they go and overlap. As this ripple overlaps with those ripples,
Yeah.
down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and then a bright spot, then a dark spot, then a bright spot. Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. You saw the ones to the right were slightly colored.
Yeah, it's
that's because
burgundy.
the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences, is different wavelengths.
Exactly.
That's amazing.
So the difference
So,
between
there's
red
so
and blue,
that red bin over there and the green part are just, I'm seeing
It's a
that and
different-
it's just different
different length.
wavelengths. And that's how we bring in all these beautiful colours all around us.
Exactly.
That's amazing. I'm amazed. Oh, good on you. Thanks,
Hey,
Ben.
thank you.
I have been enlightened, literally.
Alright, let's...
You may have noticed in that experiment that the light on the bottom of the box was not in the shape of slits. Rather, they were more kind of round blobs. And I want to know why that is. Can you write an answer for me in the comment section?
Yeah, you guys are not writing answers. Now, so for now, light for you guys is a wave. Well, as we'll dive deeper, we'll understand that light is not only a wave, but is also a particle. And we'll discuss why it exhibits properties of a particle in the next few lessons. But if you want to know more about the double slit experiment, because it's not as simple as the 1800s one, there's a lot of depth into it, you can look at these videos. Now, before you look at these videos, it's important to understand a vocabulary word that gets used a lot in these videos, and it's called the wave function. Right? The wave function, if you know in math, if you plot a wave, well, what you're going to see is you're going to see an up and down, up and down. Right? And it's kind of like what you're seeing here. Right? You have a ball that's going that's oscillating around a certain equilibrium point, the equilibrium point being the point in the middle, the line in the middle. So it's oscillating around this point. And we have a wave function that can describe the motion of this object, right? This is a wave function, and the wave function describes the motion. Well, if you suddenly stop the ball, right? If you stop the ball from moving now, what you're gonna do is you're gonna collapse the wave function now, right? You're collapsing that wave function. So if you stop the ball, there's no more oscillations, which means you can't plot a wave anymore. And the wave collapses to a certain single point that can be defined. Now, these videos are not required. I'm not requiring you to watch these videos. You may want to watch these videos if you're still curious about this experiment. And the first video that you want to watch is this video right here. It's an animation. It's a really good intro video to really just get you thinking about the double slit experiment. It has some really interesting stuff because there's things that they portray in the animation that you wouldn't think would be possible. That kind of blows your mind. It was really interesting when I was in high school. But there are a lot of errors in it. The way they talk, the way they make you, the way they lay out assumptions is misleading, to say the least. But and then after you watch this video, you want to watch the quantum eraser experiment and the single photon interference, and then the problems with the actual this video right here. So the problems with this video right here are stated in this video right here on the last video. So if you want to learn more about the double slit experiment and all the perplexities, you can watch these videos.